right, Rob Hoyt is the founder and president at Tethers Unlimited, which for 25 years has been developing products based upon space tether technologies, including solutions for cleaning up space debris and transporting people and payloads through space. Dr. Hoyt holds a PhD in aeronautics and astronautics from the University of Washington. He's arguably one of the most knowledgeable humans on tethers in space and so much more, really. He has experience in various orbital fabrication technologies and has been involved with multiple big infrastructure projects. Tethers Unlimited has been awarded many NASA and other government industrial contracts and was recently acquired by Emergent Technologies Holdings, a Colorado company specialized in satellite ground systems. Congratulations. Without further ado, Dr. Rob Hoyt.
Okay, hi, thank you. So let's see if I can share my screen. Okay, so thank you very much. Today I'd like to talk about work we have been doing on developing technologies to enable in-space services. And these fall under the category of what's now generally called OSAM, OSAM, which stands for On-Orbit Servicing, Assembly, and Manufacturing. Again, my name is Rob Hoyt, and my email is down there in the lower left, hoyt@tethers.com. If you have any questions later, please shoot me an email. So the work that we have been doing has been motivated by a desire to help create a robust and sustainable in-space economy. What we want to do is create new markets so that we can help grow the American and overall global economy. Now, there are a number of different markets that a variety of different ventures have been working to develop, ranging from asteroid resources to propellant depots, Mars infrastructure, lunar resources, space debris cleanup and recycling, microgravity manufacturing. The issue is that each of these markets by itself doesn't create a truly sustainable economy. And for example, the company Planetary Resources found that out kind of the hard way. But so they have a chicken and the egg problem where you need to be able to bring up both the service or the business at the same time as you bring up the customers to utilize those services. So for example, even if a company were right now able to go and get some asteroid resources, they wouldn't have a business plan that truly closes because there isn't yet anybody set up to buy those resources and transform them into things of value. So we see these OSAM in-space services as kind of the keystone to help tie together multiple different markets in space to be able to stand up a functioning and growable in-space economy, where people can get resources and sell them to another venture, which can in turn turn them into things of value, and then sell them to another venture, which in turn can use those things of value to integrate new kinds of space systems and then provide new kinds of services to other customers both in space and here on Earth. So we're working very hard to create the technologies to enable these in-space services. Now, we're a small company. We've been in business for 26 years now, but we don't have huge resources behind us. So I'd like to tell you first about how we have been approaching this, this very big challenge of trying to create a bootstrap, really, an economy in space. So we've been taking kind of a stepwise incremental approach to get to this big vision, where we started off by developing a handful of high performance components for very small satellites, things like CubeSats and nanosats, with the objective of trying to enable those small, low-cost systems to perform useful missions. And we've successfully leveraged some investments from NASA and the DoD and other organizations, mainly under the Small Business Innovation Research, or SBIR program, to develop some transformative new technologies such as software-defined radios, the Terminator tape deorbit device, a propulsion system that uses water as propellant called Hydros, and some gimbals and other components. And we've been able to develop those under SBIR dollars and get them on the market. And now we're in the process of ramping up our production capability, putting in all the quality assurance and other processes necessary to be able to supply these to the big government programs and commercial programs who are building out constellations of small sats. So that part of the business is now in the growth stage. For the past 10 years or so, we've been working to integrate those unique components together to create new kinds of space platforms. And that's kind of our phase, what we're calling our phase 2. And that is intended to provide networked satellite services, leveraging our unique radios and mesh networking capabilities to enable customers to put up payloads very, very easily, very rapidly, and make it very easy for them to command and get data back from their payloads. And then for the longer term, 5-10 years out realistically, we're working to create what we call these in-space services, where we combine robotic systems, in-space manufacturing capabilities, in-space assembly capabilities, to be able to stand up new kinds of space systems to provide networked communications and assembly of infrastructure for future space exploration and commercialization. And as I mentioned, we got started on a lot of these under NASA and DoD investments. So I'd like to tell you a little bit about our journey there. A lot of the work on the OSAM technologies, or in-space services technologies, originally started out under a NASA Innovative Advanced Concepts Program project called SpiderFab, where we developed a concept architecture for these in-space services, such as in-space manufacturing and assembly of very large space systems. That project got us to kind of the TRL level 3 or 4, kind of where we'd done the analyses to prove that it was feasible and that there was a net value proposition there. And then we were able to transition that project into quite a number of follow-on efforts, mostly under the SBIR program, where we developed a number of the key technology elements needed to realize that architecture, such as compact, lightweight, low-cost robotic arms, such as the KRAKEN, systems for manufacturing high-performance carbon fiber composite truss structures, a trusselator, and then things like connectors for Axon and ARTIE connectors for in-space assembly of modular space systems, and then in-space manufacturing and recycling technologies, such as the positrusion recycler, which then we were able to transition into a flight program, also funded by NASA, of what's called the Refabricator, which is up on the space station right now. It's been deintegrated and it's getting ready to be returned to Earth so we can study the results. The Refabricator combines a plastic recycling system with a 3D printer. So it was intended to demonstrate repeated recycling and manufacturing of plastic parts on orbit so that we can enable astronauts on long duration deep space missions to reuse feedstock many times to make the tools and implements and replacement parts that they need, so that they don't have to launch on a mission to Mars with huge stores of replacement parts. They can just bring a little bit of plastic feedstock and then make the things that they need as those needs come up. Additionally, we've been able to work with NASA and Maxar to put together a flight experiment called MakerSat, which is going to fly on the OSAM-1 mission in a few years. And the MakerSat is that box on the side of the spacecraft, and it is going to demonstrate in-space manufacture of a 10 to 20 meter long high-performance carbon fiber boom. So demonstrating that we can make structures in space, and it's kind of another step towards realizing the vision of the trusselator to be able to make large, high-performance truss structures to support antennas and solar arrays and those sorts of things. So we've been very fortunate to work with a number of sponsors and customers and collaborators at NASA and at some of the big prime companies to be able to take this, what started out as kind of a crazy far out vision and stepwise mature the technology elements to where we're now starting to fly and demonstrate the key capabilities. So when we talk about in-space services, there are three areas where we focus on. One is actual in-space servicing. So the idea there is having a robotic spacecraft that can provide services to another spacecraft, such as refueling, recovery, unsticking a stuck solar array or stuck antenna, or even repairing spacecraft by swapping out a broken transponder or something like that. And the main value proposition there to DoD and NASA and commercial customers is that these services can enable new kinds of capabilities for space missions, such as persistent maneuvering, satellites that can constantly maneuver without having to worry about running out of fuel, and sustainability, long-term sustainability of low Earth orbit operations, where we can deal with problems such as space debris and enable mankind to continue using near-Earth space in perpetuity. And then there's in-space assembly, where we're looking at on-orbit assembly of modular space platforms, so we can carry up a number of small kind of Lego-like pieces using small low-cost launch vehicles, and then integrate them on orbit to make large high-performance space systems. This can also be used for integration of upgrade payloads. So you can put up a satellite and then say 5 or 10 years later, when technology has matured and that satellite's payload is obsolete, instead of throwing away the satellite, you could launch a replacement payload, plug it in, and get back to making money in the space market. And the net benefit there is improved responsiveness to market and mission demands that will change over time. And then there's in-space manufacturing, where we're looking at launching into orbit raw material or even getting resources in space, and then using tools to process those materials to manufacture key elements of space systems. And the best value proposition there is for making components of space systems where performance scales with size. So by manufacturing these components on orbit, you can make them much larger than you could fit into a given available launch shroud. So you can make very large antennas, very large solar arrays, and very large structures to support things like space habitats and deep space exploration spacecraft. And the main benefit of this in-space manufacturing is increased performance per dollar, whether that performance is data throughput for an antenna, resolution for an imaging system, power for a propulsion system. The net benefit is by manufacturing in space, you can get much better performance per dollar. So now I'd like to talk to you about, tell you about some of the work we've been doing on technologies to enable in-space servicing and assembly. Much of the work that we've been doing is geared towards enabling Tethers Unlimited or one of our partner companies to build and operate a small, affordable MakerSat class robotic servicer that we call LeoNight. And this concept system is sized for cost-effective integration of MicroSat or ESPA class payloads, as well as servicing of the small satellites that are being deployed as part of many commercial ventures, as well as part of the DoD's hybrid architecture. Now, there are several ongoing very well-funded activities being funded by NASA and the DoD, such as the RSGS Geo Servicer spacecraft and the OSAM-1 NASA mission. Those systems are quite large. They're school bus-sized spacecraft, and they have giant, very heavy robotic arms. They're very capable systems, but they're designed for servicing and towing around large geo satellites or very large high value spacecraft. And they're not really economically viable for addressing the small sat industry, such as the hybrid architecture. So this Leonite system is sized to be relevant to those future architectures. And it integrates many of the high and mid TRL level technologies that I'll tell you about in a few minutes, such as our robotic arms and tool changers and collaborative control software. So one of the key elements of that concept and many of our other in-space services concepts is a lightweight, highly dexterous, and advanced control robotic arm that we call the KRAKEN. What makes this arm unique relative to all the other space robotic arms is that it integrates very precise torque sensing and control capabilities, and as well as a very high bandwidth data bus along it, so that we're able to able to monitor the forces experienced on all the joints of the arm and very quickly react to that. So we can use new kinds of control methods to implement things like active compliance, and I'll show you what that means in a minute. This design it's designed to fold up into a very compact form factor, so we can fit it onto a nanosatellite or into a express rack payload for the space station, as I'll show you in a minute. It's got a modular design, so we can put in different size joints to handle different kinds of loads, and we can make it longer or shorter. The nominal design is 7 degrees of freedom and roughly 1 meter reach, so about the reach of a human arm. And it's quite lightweight. The smallest configuration mass is about 5 kilograms, going up to about 9 kilograms if you use all large joints. But as I'll show you in a minute, that advanced control capability makes this very small, lightweight robotic arm able to safely manipulate very large, heavy payloads. So you don't need those giant, expensive robotic arms that the RSGS and OSAM-1 are relying upon. Under some NASA SBIR investments, we have worked to integrate the KRAKEN robotic arm into a express rack payload designed for the space station. And we call that payload the MANTIS Teleoperation payload. And the purpose behind this is to basically offload some of the menial and repetitive tasks that currently the astronauts have to do, and enable a graduate student on the ground to do those tasks, teleoperating this robotic arm on the space station. The arm is designed to interact with other payloads on the space station. So, for example, you could pull a sample out of a refrigerator or cold storage, put it into a biological processing unit, and then move it into a microscope or inspection station, or operate a variety of other kind of payloads on the space station. We've also been working with NASA's ASTROBee program, and ASTROBee is the small free-flying robot that's shown on the left there. And we've been developing collaborative control software called AstroPorter, which is intended to enable the ASTROBee to safely interact with other robotic systems on the space station, such as the arm, so it can do things like exchanging payloads between the two, and doing other kind of operations. So ASTROBee can act as a go fetch system, going and getting equipment for the astronauts and for other systems on the space station. Now I mentioned this active compliance capability of the robotic arm, and the importance of that is that this arm on the space station will be operating in the same volume as the astronauts. And in a traditional co-working robot here on Earth, if the robotic arm runs into a person, it will sense that and then just stop and lock up so that it doesn't hurt the person. But on the space station, that kind of approach would be a big problem, because then the arm would be an obstacle to the astronaut, which might prevent them from, escaping from a crew volume if there was a problem or something like that. So we built in this precise torque sensing and control capability, so we can enable what we're calling active compliance, where say the arm is operating and doing some kind of operation. And let's see if this video is going to play. So here we're up on the upper right, we're showing the control software, which shows the planned motion of the arm, and the arm would be going through its operations. But oh no, an astronaut has floated in the way of the arm. The arm's going to rip his head off. Oh, but the arm can sense that the force it's applying is different than what it was programmed to do, and it can actively comply, and the astronaut can push it out of the way. And then once the astronaut is out of the way, the arm can go back to doing what it was intended to do. Additionally, this active compliance capability will also be very important for in-space servicing of satellites and in-space assembly, because it enables this small, lightweight arm to accommodate errors in velocity or position during capture of a client spacecraft. So if a client spacecraft is tumbling, you can grab onto it, and that tumble won't rip the arm off of your servicing spacecraft. The arm can controllably apply force to slow the tumble down and capture the object without damaging anything. Now, for this robotic arm, we want the arm to be able to use a wide variety of different tools. So we've also developed a compact tool change interface. It's a hot swappable tool interface, so we can plug and unplug different kinds of tools without having to turn off the power. An interesting aspect of the design we came up with is that it is androgynous. So both sides, that means that both sides of the connection are the same. What that means is we can use this not only as a tool change interface, but also as a plug-in port on the inside the space station or on spacecraft. And it could serve as the base of an arm, even enable an arm to inchworm around the spacecraft or inchworm around inside a space station. And it can also serve as a docking and charging port for things like the Astra B and other free flyers. Very importantly, it also integrates safe to connect functionality. So when you make the connection, the electronics check to make sure everything is hunky-dory before you apply the high, any kind of significant voltage or power across the connections. Let's see. So another thing we're very interested in is enabling in-space assembly of modular space systems and in-space integration of payloads onto existing spacecraft. So we've also developed a little bit larger connector technology. This particular prototype is about the size of say a can of coffee. We call it the Axon connector, and it is a electromechanical connector to enable rapid pre-launch integration of payloads and on-orbit integration of payloads onto hosted payload platforms, as well as on-orbit assembly of modular space systems. This connector is also androgynous, so and an important aspect of it is that either side of the connection can secure or separate the connection. And that's important because if you've got a modular space system or a replaceable payload, you need to be able to unhook it if one side of the system has died. And this design enables that. It also integrates safe to mate sensing, and it has an interesting cover mechanism that covers the connectors when they're exposed, when the system is exposed to the space environment. So we're protecting it from FOD and atomic oxygen and other challenges. So these little movies here, if I can get this to work, just show the actuation of the connector. And this one shows the two connectors coming together they'll make the mechanical mate, check the connections are okay, and then it makes the connection. You can see the power is being transferred across it, and then it can separate and pull away. So why is this interesting? Well, one of the business opportunities that we are pursuing is in-space assembly of persistent space platforms. Now, the idea here is that instead of kind of the current way of doing business in geospace, where you build a big several $100 million school bus sized spacecraft and you have to use a giant rocket to get it up into space, all of which costs many hundreds of millions of dollars, takes 3 to 5 years, and you risk losing your whole investment if the rocket has a problem. We're looking at being able to build large, high-performance space platforms on orbit by launching many small, low-cost modules, and then using a robotic system to connect those modules together on orbit. And part of the idea here is that each of these modules can be relatively low cost. They could be single string or minimum redundancy, but by the way we've designed them to connect together and to share resources and power and do distributed control, these low cost, minimal redundancy components can integrate together to create a large system with very high redundancy, very high reliability. So this platform can serve as basically real estate for a variety of different kind of payloads on orbit, so that customers can build and launch just their payload, get it up onto orbit, and then we can plug it in and we can provide it the gaslight power and Comcast cable that it needs to operate, so they can get on orbit and operating and making money very quickly. And additionally, by mass producing these modules, we can get to economies of scale, get the cost of the modules down, so we can build large, high-performance assets using mass-produced small-sat technologies. Now, when we have these large, complex, multi-module systems, or we have several spacecraft operating together to build a system on orbit, the dynamics and control of that system is very complex. So we have been developing several software tools to enable the design and testing of control methods for these kinds of operations. And the key tool set we've developed, we call Mosaic. It's a Simulink-based environment for developing and testing control methods for satellite assembly, satellite servicing, and formation flight. And a couple of examples of how we've used it. Here in the center is a simulation of a long baseline sensing system where there's 3 small sats connected along a 20-meter long truss, and they want to reorient the truss, to point their optics or something at some other target. And here we're using a distributed attitude control system where the 3 satellites individually have thrusters and momentum wheels, but they work collaboratively to maneuver the structure and minimize any vibrations that might develop in that long, slender structure. Additionally, we've been using the Mosaic tool set to develop a set of control software to enable collaborative robotic behaviors. So this is and this is still in development, but this is a simulation of the Leonite servicing spacecraft with 2 robotic arms as it is doing a refueling operation. So here it's maneuvering one of the arms to pick up a refueling tank, and then maneuvering that to plug it into the client spacecraft on the top. And here we're capturing the full multi-body dynamics of the system. There are momentum wheels in the servicing spacecraft. And you can see that the dynamics are complex, and the simulation isn't, or this control isn't yet fully optimized. but we are successfully controlling the dynamics of this many degree of freedom system. And what we're working towards eventually is to be able to have not only multiple robotic arms, but multiple robotic agents or multiple robotic servicing spacecraft, all working together collaboratively so that you can have many small systems building a giant complex space station or giant antenna or other large system on orbit. So we're making really good progress on that Cylon effort. Now, additionally, when you have these robotic spacecraft and clients and payloads, ideally you would want them all communicating together so that you can enable these collaborative behaviors, enable them to work together safely and get the mission done. So another area we've been working on is developing a mesh networking cross-link capability suitable for small sats. We call this SWIFT-LINQ. SWIFT-LINQ is essentially an app that runs on our Flight Heritage Swift software-defined radios. So it's already TRL9, or the hardware is TRL9. The software is TRL7, and within a few months it'll be flown in TRL9. And basically what SWIFT-LINQ does is it creates a peer-to-peer mesh network between multiple satellites, enabling them to exchange data using standard IP protocols. So it essentially turns our radio into an Ethernet port in space so that you can very easily connect together multiple satellites and even ground stations all in a mesh network. So that's a mature technology, and we're currently working to improve upon it, increasing the flexibility and controllability of the network as well as the security by integrating Type 1 encryption. Now I'd like to get into talking about some of the work we've done on in-space manufacturing technologies as well as in-space recycling. I mentioned earlier the Refabricator payload. So here the Refabricator payload combined, on the top there is a plastic parts into a hopper, and those get melted down and processed and turned into 3D printer filament. And that filament then gets fed into the 3D printer in the center there. And again, it was designed not as a general use 3D printer, but really designed as an experiment to see how many times can we recycle plastic materials in the space environment before the plastic changes, plastic's characteristics change so much that either it can't be printed or it's too brittle or somehow can't serve its uses. So we've been operating that on orbit, and we're looking to get that back soon so we can look at the results. We've also done several closely related projects also funded by NASA's SBIR program. One of those is called Erasmus, where we developed processes for 3D printing, recycling, and sterilizing food and medical safe implements and tools on the space station. One of the examples there is for the space toilet on the space station. They use a little urinal funnel that's disposable. And if you were to send astronauts to Mars on a Mars mission, they'd have to carry boxes and boxes and boxes of these urinal funnels. So we had the very glamorous job of 3D printing a lot of urinal funnels to work out that process. We also developed a recyclable launch packaging material called CRISP. And so right now when they send supplies and parts to the space station, they protect those parts in foam and bubble wrap and Ziploc bags and those sorts of things. And once on orbit, those things become trash that the astronauts have to find somewhere to store. So they're like shoving them in the corners and behind stuff. And that ends up being kind of a safety hazard because a lot of that stuff is flammable. So we've developed this recyclable launch packaging material using 3D printing processes. We can make customized boxes and other kinds of containers, and all that stuff is designed to be recycled in the Refabricator so that it can be turned into new things that the astronauts will need. We have also been working with NASA's in-space manufacturing program on a project called FabLab, where we're developing, and we and they are developing an integrated capability for precision manufacturing of metallic parts for mission critical applications. And this system will integrate things like multi-material and metal 3D printers, possibly a zero-G CNC system that we developed called Mamba, recycling systems, inline inspection capabilities. So as you're making the part, you can voids or any other defects. And then robotics such as the KRAKEN arm and the MANTIS system for moving parts in between stages. Some of the technical challenges there that are yet to be really worked down is, how do you integrate the inline inspection into the manufacturing process? How do you do metallic additive manufacturing in zero-G? There are a couple other companies have been working as part of this project, and they've made really good progress there, but there's still maturation needed to be done. And then for a lot of metallic parts and metallic materials, there's heat treatment needed to get to the structural or other performance that you really want out of the structure. And then, how do you do that in a zero-G environment where traditionally those heat treatments often involve heating something up and then quenching it very quickly in a liquid such as oil? How do you do that in zero-G? That's yet to be really worked out. And then the other main area of in-space manufacturing we've been working is in-space manufacturing of space structures. And here on the left is a time-lapse video of an early prototype of our trussulator device, manufacturing a carbon fiber truss. This sample ends up being about 10 meters long. It's extremely lightweight, it's extremely stiff, so it's self-supporting in zero-G, and you can actually wave it around like a giant lightsaber, and because engineers are engineers, of course, they did that. But we're right now working to assemble. We've designed and we're currently assembling the MakerSat system, which will fly on the side of the Maxar NASA OSAM-1 spacecraft. And the MakerSat payload is going to do in-space manufacturing of a stiff, thermally stable carbon fiber composite boom, at least 10 meters long. We're hoping to shoot for 20 meters. And then it's designed so that the robotic system on OSAM can actually pull off the payload and wave it around like a lightsaber or just toss it away. The carbon fiber composites are important because they enable the near zero coefficient of thermal expansion performance that you need to be able to build thermally stable astronomical platforms such as giant telescopes for imaging exoplanets and that sort of thing. Initial aspect of the experiment is we have integrated metrology. So as we're manufacturing this boom, we're going to be measuring both its straightness and also its stiffness, kind of bending it and vibrating it so that we can check that it's got the same structural performance as similar structures that we make here on the ground. And that program had completed CDR back in the summer, and we're currently in assembly, looking to get the main parts of the payload completed assembly this month. And that's due for delivery to Maxar and NASA in the middle of 2021. And then final thing I'd like to tell you about, we have been working under some investment by DARPA to develop a payload called OrbWeaver. And OrbWeaver is intended to demonstrate in-space recycling and manufacturing relevant to remediation of space debris. So the OrbWeaver payload is actually a couple of payloads. One of them is the Leo Knight servicing spacecraft, and the other is a casting and nibbling system. And it's designed to ride up into orbit on an ESPA ring. An ESPA ring is a big aluminum ring that goes between a rocket and a large satellite, and you can put a bunch of small satellites on the ESPA ring. Now, after that ESPA ring has released all of its small sat secondary payloads, typically it would become space debris that would either junk up orbit or you'd have to get rid of it. In this project, the Orb-Weaver payload is going to ride on the ESPA ring, and after it's released all its other payloads, the Orb-Weaver is actually going to chew up most of the ESPA ring and then take the metallic chips and reprocess them, melt them down, and cast them to make hexagonal reflector segments. And then the Leonite robotic system is going to assemble those hexagonal reflector segments together to make a large high-performance antenna reflector and integrate it with RF components, which are based on our SWIFT software-defined radios, to do full in-space manufacturing, assembly, and integration of a high-throughput tactical SATCOM satellite. And the overall objective of this project is really to do kind of an end around on the space debris problem, where we've been working on space debris solutions for 25 years, but we found out the hard way that nobody wants to pay to clean up the space debris environment. All of the government agencies are like, it's not my job. So we're trying to do an end around on that problem and come up with a way to turn space debris into a potentially profitable resource. So we can, if we can demonstrate in this experiment that we can transform an ESPA ring into a antenna with high value, then potentially a future business venture could go up and clean up the space debris environment and actually make a profit at it. So I think I've come to the end of my allotted time. I'd like to thank you all for your attention. And I'll be, again, my contact info is in the lower left there, and I'll be happy to try to answer any questions you have.
Dr. Hoyt, thank you very much for joining us today. This was really interesting. We only have about 2 minutes, 3 minutes to stay on schedule before we switch it over. So I wanted to tell you, I have a private chat going on my screen while you're talking with some of the folks that are attending. And there's one high school kid, I'm not gonna call him out, but there's a guy on this call that is so excited about the work that you're doing. I have been talking to him about robotics in space, and so all of a sudden, all the dots connected for him. So he is. I am going to be sharing some conversations with him soon. I think he will be, reaching out to you as well. So just kind of expect that. There are some folks that are really excited about what you're doing.
Okay, great.
There's also been a comment about how. Everybody assumes that this is still in the engineering phase, and it's clearly not. I mean, you are in an engineering phase, but this is real world technology. These are the nuts and bolts for building the next space economy. So really, really tremendous that you're doing that. I'm going to ask just one question fast. We have 2 space lawyers on the call right now, so no surprise there. What policy changes do you think could be either obstacles or opportunities for space OSAM operations?
Well, one of the biggest challenges for the debris remediation and debris recycling is there's a big kind of international diplomacy and policy issue that you can't go and touch a space object that was launched by another country unless they agree to it. So right now the biggest threats are a number of Soviet rocket boosters that are in kind of problematic orbits. But even if we had the capability to go and get them and remove them or recycle them, going and touching them would actually be considered an act of nuclear war. So that's well above my pay grade, but I'm hoping that our leadership can start to work with other countries and figure out a path forward there. And then beyond that, we need to figure out you know, if you create a business in space and your customers are in space, how's that taxed? How are the profits there taxed? And you know, that ideally should be well defined, so that investments can be made there without a huge amount of risk.
Terrific. Thank you very much. We're going to continue this conversation. Dr. Hoyt did provide his contact information, and I'll be posting it in the chat in just a moment. We're going to switch it over to Lila. Thank you very much, Dr. Hoyt. Appreciate your time.
Thank you.
Thank you.
Thanks again, Dr. Hoyt. Thank you everyone for joining us. This is Blue Marble Week.